What we're going to do today is we're going to learn how to integrate functions that aren't as straightforward as just raising the power and adding a constant at the front. So we're looking at functions that are functions of functions and how we can reverse that, or the product of two functions where one function is the derivative of another one. So if we turn our attention to the integral over here, what we want to do is we want to integrate this. Now, if we just use our stage one techniques, we might be able to see a relationship and might be able to put forward a conjecture of what we think the answer is and then just work our way backwards and be like, yep, we're good. But there's a simpler way to look at this. Firstly,
He's lost his phone.
welcome, Rowan.
Hello.
We missed you.
Thank you.
You've come at the right place because what we have over here is a function and then we have another function multiplied together. Now, how do these two, so the insides of these two functions, relate to one another?
The second bracket is the derivative.
Yeah, this one is the derivative of what's on inside here. So what we're going to do is we're going to use something called substitution. First thing is I'm going to write this as a bracket rather than a radical. So I do my best integral symbol. I open a parenthesis and I raise it to the power of a half. And then I complete the expression. Now here's where the magic's about to occur. I'm going to get this expression here and set it to a variable called u. And then I'm going to differentiate u with respect to x. So I'm normally going to write du over dx equals 4x to the power of 3, take 3. However, I'm going to write it slightly different. See how I've got dx down the bottom? For this time and this time only, I'm just going to write this is du. And I have my derivative here multiplied by dx. Almost as if I'm getting ready to integrate this, but I'm not. Now, this is really practical because have a look at what we have above. In orange, underline, we have this guy here. So this is going to be u to the power of a half. And then, conveniently, 4x cubed minus 3 times dx appears here. So all of a sudden we have this method of simplifying the expression we're trying to integrate without doing the integral just yet. So writing this out, we're going to get the integral of it's going to be u to the power of a half dot du. How much simpler does that look? Quite simpler. Now we know how to integrate this. We simply raise the power by 1 and then we figure out what we needed to put there as a constant. In this case, whoops, we don't need that. We raise u to the power of an extra 1, so it becomes 3 on 2. And if we were to take the derivative of that, then we would have got 3 on 2 over here. So we go 3 under 2. Simple stuff from methods, but our value for u is x to the 4 take 3x. Welcome, Foreman. So we're going to get x to the 4 take 3x all to the power on 3 on 2, and life is good. Now if we wanted to write this with our radical symbol, then of course we can do that as well. It's just 2 over 3 and then inside a radical we're going to have the x to the 4 take 3x raised to the power of 3. And what did I forget? Plus c. Plus the constant of integration. Correct, and you get double points for something looking very sophisticated. So this over here is what we call integration by substitution. We use integration by substitution when we see that we have an integral where the integral is the product of the derivative of one of the inside functions. Is that cool? 2 more. One indefinite integral, one definite integral. Seem like fun?
Yeah.
Okay. Did we get this down?
I haven't, no.
Alright.
They can get 100% of this integration test as well.
Be better.
This always appears in the this or one of the other ones always appears in the external. I guarantee it will appear in the internal. Because there's only 5 types of, no, there's 3 methods we're learning.
Yeah, what the test? It must be really soon.
Yeah, week 3. I was doing the practice test last night.
Oh, here he is. He's teacher.
Did you hear he got 100%?
Yeah, I did.
Oh, you've been sick there, mate.
No, is that something you
Well,
want to
there
do?
Well, we're going to sit at
At the table.
the head of the table.
Best goes at the head.
What?
Best goes at the head.
It's on. It's your topic now, apparently.
You get up there and teach it.
What was that?
You get up there and teach it.
Okay, we're going to go
You
B.
can actually teach us all how to teach.
And I'm going to do it, I'll start it off up here. It will be, you want something similar or something different?
Similar.
Different? Okay. Okay, this is one. X times e to the power of 3 take x squared. Okay, let's have a look. First thing we need to do before we think of, or before we propose any way to integrate this, is we need to think, what do we have presented in front of us? Is there any relationship between the factors in this integral?
What did you say?
Is there any relationship between the factors presented in this integral? Because we're going to have 3 new methods to integrate soon. We have to figure out which one we're going for.
What's the dot between the x squared and the dx?
Times. Good question. What happens if we what happens if we differentiate x?
1.
1. What happens if we differentiate e to the 3 take x squared?
-2x.
-2x. Is there any sort of relationship between this and that?
No.
Think about it.
-2 times -2.
Negative 1.
Can we see the relationship?
Why is it negative a half and not half?
Sorry. we see the relationship now? The first one is the derivative of the second factor. In the top line, the first factor is a dilated derivative of the second factor. So because we have two factors and one of them is a dilated derivative of the other one, what method of integration are we going to employ here? Substitution. Now the question is, which one do we set to u? Let u equal this or that.
That,
Why?
because then you get the du thing.
Bingo. So, boom, take the derivative. Rather than saying du over dx, we just say du is
Oh,
minus 2x
I don't know.
times e to the 3x squared dot dx.
What is that?
So all of a sudden, no, that's not right. There we go. Okay, all of a sudden we've got something convenient. Now, looking at this. If I sub u into here, how am I going to deal with du? I'm going to have a problem, aren't I? So let's just focus on du. My du is minus 2x e to the 3 minus x squared. Does that appear up here at all?
Oh. That's
It does. So am I going to sub in u? No, just du. What's the integral of du?
you.
U. Do we know what u is?
Yeah.
What is u?
A to the 3x a to the 3 take x squared.
Boom shakalaka. You picking up what I'm putting down? You liking it?
Wait,
Yeah.
that's sick.
Imagine all the things you can integrate now.
Wait, what?
It's limitless.
Oh, it's not-
Wait, myself, why didn't we do this in methods?
Too complex.
What?
Not enough time, like too much content.
No, okay.
New South Wales, they teach this to their equivalent of methods.
Yeah.
Yeah, but they don't. Oh, back when I did, they didn't do the statistics.
You should have gone for the top
Or you can just learn now.
But yeah, not too hard, but very powerful. That's like the ideal position to be in math. Okay, one more, and we'll make it a definitive integral. Did we get this down?
Yeah, yeah. I got the last.
Okay.
I didn't get 100%. Got 98.
Pi on 6 and 0.
Where'd you get it?
And finally,
Wait, no, we need to.
just for fun,
What were your count marks?
I'm sorry, do we want to
want to compare them? Do you want to bring up the last one then after you compare?
Mad Dog, you ready to integrate this?
Yeah. Ready.
What are we going to do here? What do we have?
Definite integral.
A definite integral. When you say a definite integral like this and it just says simplify, what would you do normally?
Fundamental theorem. What?
Pardon?
Calculator.
Is that not what it is?
What did you say?
The fundamental theorem in calculus.
What?
Is that not what it's called?
I don't know what that is.
On the
No, I don't know what
Are
you're
you saying
saying.
it from the text?
I'm
That's
pretty
what
sure
it's
that's
called.
I'm pretty sure that's what you're adding to it.
No, I
because
think- Is that not just, yeah, that's just when you
Add two
integrate and
definite.
solve it,
is that not what you did?
yeah. Yeah, no, you just put it in your calculator.
Yeah. Isaac's the man for this. You just pick up your calculator and you put it. But today we're not doing that because we're doing a method activity to improve our integration.
We would get one that's like solve this algebraically.
That's it.
Yeah, of course.
And is that sine cubed x?
It is.
Oh, never seen before.
Ooh. Now, does this fit the criteria for integration by parts?
By parts.
Yeah. Sorry, not by parts, by substitution. By parts is tomorrow.
Tomorrow.
Tomorrow's lesson.
Tomorrow's Sunday.
We're coming in.
I only count days as the days I do spec.
Ah, fair. That's so fair. What a calendar.
Yeah, hold that like
Does this fit the criteria for by substitution?
Not right now.
Not yet. Because we just got one function. We sort of have two because we could put a 1 in there, but that's not going to help us. So you could go 1 times sine cubed, and that might work in some situations, but not today. Instead, we need to modify this. Now, I'm going to tell you that this one can be done by substitution, but in the test, you're going to have to figure it out on your own. Yes, Rowan?
Because this sine is cubed, does that mean the whole function's cubed? So the whole sine x is all.
Yeah, so it's sine x all cubed, but we put it up here because it's ambiguous if you put it there.
Yeah.
All right, so what we're going to do is firstly, I'm going to break this. Pi on 6, 0. We're then going to go sine squared x sine x dot dx. Okay, does this now almost fit the criteria for by substitution?
Yeah.
Nearly there. Consider that sine squared x is the same as writing 1 minus cosine squared x. Hence, okay, now let's look at what we have, something very different to what we saw before. Does one of the factors look like it's almost the derivative of the other factor?
Almost.
Yeah, cos squared, I don't know, something to do with that.
Something with the cosine and the sine. What's the relationship between cosine and sine in terms of derivative?
They alternate?
Yeah, they alternate. Let u equal cos x, hence du is going to be negative sine x dot dx. So when we make the substitutions here, we're going to get pi on 6, 0. Inside the bracket, we're going to get 1 minus u squared times, and this one is going to be, move the negative from there and put it there. It's going to be negative du. Could we integrate this? Of course. We're going to get 1 dot du plus, actually it's going to be plus, that one's going to be minus because there's a minus on the du. Okay, then it's going to be u squared dot du. We can easily do these integrals. It's going to be minus u plus 1 over 3 u to the 3. And then I've done something a little bit silly here. I want you to think, I changed the value for, we're not integrating with x down here, we're integrating with u. But I did not do anything to the bounds of integration. Should that matter? Probably, because if we sub this into u, they're not going to make any sense. So instead, I always do this at first. I should have changed them. I'm going to call them a and b for now. What are a and b? Different values. Do I care what a and b are? Sometimes. Okay, so we can do the integral right there. And rather than setting a and b, what I'm going to do is I'm going to leave them as a and b while I'm in the space of u, and then I'm going to change u back into x. So we know that u is cos x. Why? Just cos. Then this is going to be pi on 6, and this is 0. So when we evaluate this, we're going to hopefully get cos pi on 6 plus 1 over 3 cos cubed pi on 6. Take away okay, cos pi on 6 is root 3 on 2.
How did 1 take u squared change to 1 times du plus pi on?
Do you see how this should have been negative sine x dot dx?
Yep.
And then I moved the negative in front of the du.
Yep.
So every time I see this, I change it to minus du, so it's minus du. Now, as a consequence, when I split this integral apart, the negative goes on the 1, so it becomes minus 1. And that negative u squared becomes positive u squared.
Okay.
Does that clarify?
Yep.
Awesome.
I was to say, it literally has the tracking number. I just seem to know where it is. Also, did she really ask about you? Because she literally said, I know who has you, and then I proceeded to tell her everything. I don't, that's more of a, I don't care.
No, I think she has no idea. He
think
had
she
no
had
idea what was
trouble?
going on. Who? He told her like everything he does through her is it. And they tried to get him to something. He exposed everything he does.
Wow, I
She's
said,
like, how many
she's
times
like,
he's out of
hey.
the house, and he's like, just for soccer, like Tuesdays, Thursdays.
Why are you
Sunday
saying like
mornings."
that?
That's what he's like. So she's gonna get you Sunday morning.
Okay.
Do you guys get 2 on 3?
Yeah.
No, you did not.
I did that.
Did you, Nick?
No, not yet.
What'd you get?
I got it, yeah.
I think that's right. It's going on YouTube, so it must be right.
Found in the calculator?
Yeah, we probably should just put it in the calculator.
Is everything you put on YouTube correct?
sometimes.
Wait, YouTube clips all your mistakes as well.
Does it?
Yeah. Every time one of us corrects you, it's on YouTube.
Oh yeah. I don't always get corrected.
What's the answer?
Right, can I see it?
Well, the calculator says it's not the right answer.
So what do you reckon? Do you think the calculator's wrong?
I think so.
But that's a good answer.
There's just so many places that someone can make a mistake.
Yeah.
The integral's fine.
It's when you've tried simplifying it out.
Whereabouts?
In your second to last line, I
This one?
think. No, the one above.
Yeah. Because pi on 6 is root 3 on 2, is it not? It is. Oh, sorry. I forgot to cube the 2. So this will
That's why it's
be
this one.
8, 3 8s are 24.
Tell me about lazy
Probably not, but like, sure. According to who?
The 3 cancel with the root 3 there.
Yeah, it's a good funky answer.
Just gonna put this one in the calculator.
It's hard then, Adam.
A little bit, for no reason. Went to bed at 9:30.
I fell asleep last night without even being ready for
What?
bed.
How's that even possible? Wait, what?
Fell asleep last night
Like,
without getting
you were
ready for bed.
sleepy at like 8:30.
Like getting ready for bed.
Yeah.
I was still in like all my clothes and stuff, and I haven't brushed my teeth or anything. I just laid in my bed and then woke up in the morning.
Okay, so what does this answer tell us, Rowan?
That's a messy answer.
Be more diligent like the boys at the front,
Uh,
because they're figuring out where I made the mistake.
it's divisible by 24.
What?
That answer.
Okay, so this is integration by substitution. It allows us to integrate functions that are the product of a function and its derivative, or its dilated derivative. We do it by picking the one that looks like the derivative and setting it, we do it by picking the one that looks like the non-derivative function, setting it to u, taking the derivative, and then subbing u and dot du in. Sometimes you don't just sub in u, sometimes you just sub in the du and then get the u back at the end. Seem okay? When you are doing definite integrals, remember you must change the bounds of integration either by substitute the upper and the lower bounds into u and then find the subsequent values, in which case you don't have to go back to x, or just do what I did, set a and b. You probably should define what a and b are. They're just real numbers. In our case, they can be complex. But substitute a and b in until you go back into the domain for x, in which case you substitute the original bounds of integration in. Any questions? That's as hard as it's probably going to get.
It looks really difficult.
It's
So
not.
what's the A and B for? The bounds? How come they're not the same?
Do you see? So we go from known bounds of integration to unknown.
Yep.
What happened between this line and this line?
We use.
Yeah, we substituted in u. When we change what we're integrating with respect to, the bounds of integration should also change.
So why do they end up cancelling out or something like that?
We put them back in because we move away from u and back to x, in which case we can reuse our original bounds of integration.
Oh, okay.
Seem cool?
Yeah,